We saw in the earlier class the arithmetic operations using vectors, right? So we discussed about the addition of two vectors. Okay. When you add two vectors, one of the important condition is both the vectors should be same physical quantity. Okay, you can't add a velocity with a force or something like that. So both the quantities should be, both the vectors should represent the same physical quantity. Only that you can add. And we also saw we saw that you can multiplying a scalar with a vector will be a vector. Only the magnitude will be larger. Whatever will be different. Okay. And okay, this is what things. So now we saw a detail about the addition of vectors. Now there are cases you can multiply vectors also. Okay. Before that, tell me what is that we saw? The property multiplication of a scalar into a vector will be what? Oops. Just yeah. All right. Scalar into a vector, correct? This we saw. That will be what? Vector. Oops. Vector. Okay. So then second one is scalar into a scalar. Will be a scalar only. Okay, there are examples. For vector, what happened? Force. Oops, sorry. Force. It is mass into acceleration. Okay, so this is a scalar and this is a vector. Here, product of the two scalars, power. Energy divided by time. All are scalars. Okay, or suppose if you have the power and if you want energy, energy is equal to power into time. Okay, these all are scalars. Okay, so these are the product operational scalars. Now, what happens? The question is, what happens when you multiply a vector into a vector? What it will be? Tell me what it will be. Guess. Okay, fine. It should be a vector, correct? Okay. So I am giving you an example. You are done, right? Equation of what is the force? Sorry, work done. Isn't it? You know the work done. The work done is when you apply a force on an object. Okay. If you moved by a distance, then you know the work is done on the object, correct? So, and force is required for the work to be done. Am I right? So, okay, what is the formula for work done? Work done equal to force into displacement, correct? So, displacement will be what? Say something like S. Okay. So, tell me force into displacement. Force is a vector. Displacement is also a vector. What you have done? You have multiplied and but work. So this is a vector. This is a vector. And this is a scalar. Okay. So what is that? When you multiply two vectors, it's a scalar. Sure? So I am writing scalar here. But then I can have another thing also. Fleming's left-hand rule. What happened? You have a loop current or whenever, okay, I'll draw we have a magnetic field line here. Okay, magnet fields have a direction. Am I right? Huh? So you're having a current carrying conductor. Whatever I call. So magnetic field, what is symbol you use? H or B. Okay, let us write it B, whatever. Okay, so this is a vector. I is a vector. Okay, so what happens? Fleming's left hand rule? This magnetic field? Correct. So what happened when your magnetic field and the current are perpendicular to each other? So then, so suppose what is that? This is the current, right? Yeah. So then there will be a force acting on the conductor which moves down. Okay. So that force. So here, what is the product? Because of I, current and your magnetic field, you are going to face a force. Okay. So here what happened? You are basically means you are trying to multiply. This is, when you see it, multiply of two vectors. Two vectors combinedly, it's going to cause a force which is also an vector. So now, so I can say here you say your two vectors when I multiply, it can give a scalar. But here, a current into magnetic field will give you a force that is going to be perpendicular. That has a direction. Force is a vector. So this can be a vector also. Am I right? So therefore, when you multiply two vectors, two things are possible. It can give rise to a scalar. That's what we saw here. Always, if you see in a Fleming's left hand rule in a motor, okay, because motor, see what happened in a motor, you simply take a motor, you're passing a current have a direction, and magnet is there, magnetic field have a direction. Your motor spin, that's a force, that's also having a direction. Okay, the moment you pass on a current, so current and the magnetic field will cause us rotation in the motor. So there everything is vector. The product of a current into magnetic field is also giving a vector, the vector force. So therefore, product of a vector, multiplication of a vector can be either scalar or vector. Okay. So, and only thing, if you remember, when you multiplying vectors, are we bothered about they both should be of same physical quantity? No. Okay, for a multiplication, it is not necessary the vectors should be of same physical quantity. Okay, so then therefore there are two different cases of vector multiplication. Unlike your scalar, when we say there is only one multiplication, because scalar into scalar gives you scalar. Only thing, when it's become a vector, there can be two answers. The answer can be a scalar, or let's say the answer can be a vector. So first let us see the scalar one, that is this one. When you multiplying a two vector, when it gives rise to a scalar, that you call it as a scalar product. What? Scalar, or what they call is a dot product. That's also one way. Dot product. Okay. So in this case, in a scalar product, what they do is you take a vector. Let me call a vector. A is a vector. And B is also another vector. I am going to multiply these two vectors. As I said, force into displacement, that gives you energy. So when I multiply these two vectors to form a scalar, and that multiplication you call as your scalar product or dot product. What is the symbol they use? A vector dot B vector. So this dot is a symbol. Okay. So whenever you take this is what you call a dot product. Whenever you take a dot product, so then the resultant will be some scalar. And what will be the scalar? Scalar doesn't have a direction. So resultant will be the magnitude of A vector into the magnitude of B vector into cosine of the angle theta. Theta is angle between A and B. That means what? Let this be the vector A and this be the vector B. So this angle theta.
What is the parallel?
Yes, we will come. We will see what happened. It's parallel. Yeah, correct. Good question. We will see that. Okay, so this is called as your scalar product. Okay, and all in your earlier classes, You multiplied the force into displacement, everything you did without being bothered whether they are scalars or vectors or something. Okay, in reality, when you're dealing with physics, you should know is it a scalar product or a vector product. Okay. Well, yeah, we'll come to the theta. What is that? Okay, so when it will be parallel, anti-parallel, all those things. Okay, so or perpendicular, all those. So and so fine. Okay, so then A dot B equal to AB cos theta. So the way you can look at it is, for example, okay, let me take, suppose, if you remember, last time we resolved the vectors. Did you remember? We resolved the vectors also, right? If you have, this is an R vector, and if this angle is theta, what is the component of vector along this line?
I.
Okay, this is I know that, I cap. What is the component of vector along this axis?
Oh,
Correct? And what about this?
R sin theta.
And
R sin theta and J.
J cap. Okay, so this is the component. So take any vector, the component along another vector, that is here the vector is I cap, will be R cos theta. So its magnitude is R cos theta, this magnitude is R sin theta. Okay, so now if I ask you, what will be the component of A vector, magnitude of A vector along B vector? So let us say, for example, so B vector I am going to give a direction as UB cap. So give me the component of A vector along UB vector.
A cos theta.
Correct. So the component of A along B vector would be A cos theta into UB. Correct. So now, so basically so there is another vector. This is B. Okay, this is a B and UB. So what it says, your scalar product is nothing but A cos, if you multiply both the magnitudes, you bring the vector to the same direction, okay, get your vector both along the same direction and multiply the magnitudes. What happened? Now what is the magnitude of this? A cos theta into B. So this makes AB cos theta. You can do it the same way, opposite way also. Because see, now your question is, why I took a component of A along B? Correct? You can do, I don't like this B. So I want to have UA. Okay. So what will be the component of B along A? B along A.
B sin theta.
Sin theta?
No, that will be cos theta.
Cos theta. Correct. Because sin theta will be cos theta. Cos theta into UA. Again you multiply them both. So here it is A, UA. Okay. So multiply the magnitudes. What happened? AB cos theta. That's what. Okay, so the scalar product is what? When you say a scalar product, take the component along means what happened? You make if you have scalar product between two vectors is something like you take the component of one vector over the other, means so that they have the same direction, and multiply the magnitudes. Understand? So that's what all your scalar product is. Okay. So now, and there is an interesting property. So then what I can write? So a scalar product can be written as A dot B is equal to AB cos theta, or we can write it as A into B cos theta. That is what this is. A B cos theta is the component of B along A. Correct? Or I can also write it as A cos theta into B. Or you can say component A along P. It doesn't matter. Okay, because why it doesn't matter is you are not bothered about the direction. Okay, so you want to just multiply the magnitudes. So what happened? Get all of them in the same direction, multiply the magnitudes. And that's what you call as a scalar product. Okay, and now you can see scalar product. Well, now you tell me whether the scalar product is commutative. Is that A dot B equal to B dot A?
It is.
It is, yes, of course. Because the angle is same, na? Okay, so what is that? We can write. So simple. What way we can write is A dot B equal to A into B cos theta. Okay, or you can write it as A cos theta into B, or B A cos theta. Okay, that's equal to B dot A. Okay, because A is a component of A cos theta is the see here what happened. A cos theta is the component of A along B. Okay, and here B cos theta is a component of B along A. So since both are there, it can be commutative also. Okay, so scalar products are commutative. Okay, is there anything? Yeah, it doesn't matter. Fine. So basically, yeah, that's right. So it's a commutative property, or in a book they written as AB cos theta or BA cos theta. It doesn't matter. And okay, now the second question is, are the scalar product distributive? Distributive law of multiplication. Correct. So what will be distributive law of multiplication? What is that? Suppose you are having A vector dot B vector plus C. A vector dot B vector plus C vector. This will be A vector dot B vector plus A vector dot C vector. Is that, can you write like this? Yes, of course. Okay, you can do. Okay, so you know the addition of two vectors. You know what the addition of two vectors. Take out the component of the vector. I am not going to prove this. We can prove it. Okay, then there are special cases of scalar product, as you said. You are asking what happens when your theta is parallel to each other. Okay. A simple case I can tell you when it is parallel to each other is you drop a stone. Okay, when you drop a stone down, there is a force that due to the acceleration due to gravity, correct? That's what mg. And the stone is also getting displaced. That's also along this direction, correct? So what happens? So they both are, what is the angle between them both? Zero, parallel. But this is not always true. If you have a slope and if you are if you put a ball in it, the ball rolls down, correct? Here displacement is along this direction, whereas the force is this direction. Okay, and only a component of force will act on it. You got it? So both are not same. That's what here it is. So what happens? So there are cases when the angle becomes certain theta, when the angle becomes 0, and sometimes the angle can be opposite also.
Gravitational force.
Against, yeah. Okay, so there you are. Okay, so let us try to find the case of. Okay, so there means your product will become negative. I will show you. So what happened? Correct. So AB cos theta. So for example, if a theta is equal to 0, so then A vector dot B vector will be AB. Am I right? Because cos theta equal to cos of 0 degree equal to 1. On the other hand, if theta equal to 180 degree, that is this case. Just multiply the mg and that's why you say the potential energy, correct? What you call, when it has moved over h, you just multiplied mg h. Okay, remember, h is the displacement. Okay, when you find out the potential energy or the work done, when it reaches the work done is mgh, right? G is a vector, h is a displacement, right? It has a direction. H is not a distance, is a displacement. Okay, so it's not just a distance, it has a certain direction. So this is again a scalar product. Can you understand that? Because G is a vector, H is a vector. So that's why you are getting this. Okay, so there you normally don't take into any cos theta or something because you are taking all the theta is 0 there. Okay, now on the other hand, when you throw the stone up, or you pump a water to a tank. Okay. So then when you're pumping a water, there's a force, acceleration is acting downwards. On the other hand, you're giving a push upwards. So displacement is negative. Right? So what is the angle between these two? See, you see, your force is pulling it down. But is it the water flowing down or you're pushing up to the pump? So the direction is above. Okay, so your displacement is opposite side. Correct? Your work done is what? Work done equal to force into displacement. Okay, so force into, it's not force into F dot according to vector law. Okay. So here they both are same direction. So your theta is 0, we got A into B. When it is opposite, that means when you throw a stone upwards, the force is acting downwards, but your displacement is upwards, 180 degree. Got it? So 180 degree, in that case what happened? Tell me, what will be A dot B? Will be same? Cos 180 will be what? Same? Cos pi degree is what? 1 or minus 1? So this will be what? Minus A into B. So in this case, this is very interesting. If they are along same direction, you get the dot product to be positive. If it is the opposite direction, the anti-parallel, then your dot product is negative. So when you do a calculation, when you are moving it upwards, when you calculate, so the sign says whether you are doing work is done on it or work is done by it. You got it? Or you're pushing the stone upwards. That means the work is done on the stone. If you leave the stone, the stone falls down. The work is done by the stone. So the sign dictates the property, whether the work is done on it or the work is done by it. Okay, so this is an interesting case of a dot product. So now tell me, is there a way, if theta equal to 90 degree, let us say the condition, theta equal to 90 degree. What is cos 90 degree? Tell me. 0. Under the case, what happened? A dot B will be 0 cos 90. Okay. So this is, and this happens. This is correct. Now, left hand rule is different. Left hand rule is, resultant is also a vector, but it is a scalar. In the left hand rule, Fleming's left hand rule, all the product is also scalar. We are not looking into that. That's the second case. We are looking into the first case where the product will be a scalar. So this is right. I'm asking you a question. Can you move a stone or anything perpendicular by applying a force like this? You are up, okay. So you are pushing a ball. Can the ball go exactly perpendicular where the direction you pushed? Or you got it. Don't spin the ball, you kick the ball straight. Can you kick the ball such that the ball goes perpendicular to you? Can you kick? Your force has to be applied exactly on the ball. You kick sideways, that's okay, you can do. Okay, so when you kick a ball or when you hit a ball or when the billiards, when you hit the ball with the striker, so the ball goes along the direction only. You hit it, with the ball go perpendicular? It can't. Okay, so now therefore means that's what the product says. A dot product says 0. Okay, the work cannot be done on the perpendicular to it. If any force is applied and if there is a displacement perpendicular to that force, then the work done is 0. The force has not done any work because the force cannot push it perpendicular. You got it?
But
So
what if in a case like if I shoot a gun perpendicular, then the bullet will go in the straight direction.
correct,
But the gravitation force will push it down.
correct,
And the work done will eventually put the bullet in the ground.
correct,
It
correct.
will work.
See, the point is what I'm saying is when you fire the gun, the bullet is moving. Okay, so what the point is, you fire the gun, okay, and the bullet just fall down from the tip. Can you tell me whether the gun has done any work? You take the bullet and drop it. That's also going to fall down. Correct? So that's the point I'm saying. If you're applied a force and what you see, the force has not caused any displacement along the direction of the force. Any component, okay, or just it gives a force just perpendicular to it. That means this force has not done any work on that bullet. The bullet has not hit, your trigger has not fired the bullet. It doesn't misfire, the bullet just drops. Okay. You got it? So that's what I mean. So whenever the displacement is perpendicular, or any cases, so this is for force and perpendicular, in any cases, if any two scalar products, any two vectors, if the two vectors are perpendicular to each other, then their dot product will be always 0 because angle is 90 degrees. So one example is that I was saying force and the displacement. Okay, so this is what your dot product with the, okay, fine. Good, yeah, so then, okay, so this way, so now can you tell me what will be your I cap into I cap, you know what is I cap? Along the x-axis. What this will be?
In the same direction.
Correct. So what is the angle between I cap and I cap? 0. So cos 0 is 1. So this will be what? Equal to 1. A into B what? It's a unit vector. It's a unit vector magnitude is 1, na? 1 into 1. Am I right? So the angle between the two vectors are 0. So no issues. Okay. And what about this one? So 0, yeah, because I and j, they are perpendicular to each other, na? So cos 90 will become 0. Similarly, you can put up I cap into k cap also will be 0. And similarly, you can say j cap into j cap will be equal to 1. Any vectors on the same direction, unit vectors, take a dot product of unit vectors on the same direction will be always 1. Dot product of unit vectors which are perpendicular to each other will be always 0. Okay, so clear this one. And yeah, okay, the scalar product of vectors expressed in terms of rectangular components. Yeah, okay, they are taken at 3 dimension. I will show you that. Fine. Okay, so now, okay, so this is okay. The last class we saw how to resolve a vector in a rectangular components, right? Because a parallelogram law or a triangle law says two vectors can be written as a resultant of one vector. So the same I can say any resultant, any vector can be resolved into 2 vectors or 3 vectors, whatever it is, for the dimensions. So we can resolve any vector A into along its x, y and z. Correct? So that means what? Ax is the magnitude along x-axis into I cap plus Ay is the magnitude along y-axis into j cap plus Az into along the z-axis, k cap. Okay. So let me have B vector equal to similarly Bx I cap plus By j cap plus Bz k cap. Okay. Now tell me, what is A vector dot B vector? Okay, what be A vector dot B vector? Let us write it. Ax I cap plus Ay j cap plus Az k cap dot product of Bx I cap plus By j cap plus Bz k cap. Okay, so we know the distributive law works, right? So then what happened? So we have to multiply component by component. So what happened? Ax, Bx, magnitudes you can simply multiply. I cap dot I cap. Yes, correct, will come. So then Ax, By, I cap dot j cap. Okay, plus Ax, Bz, I cap dot, because I cap and k cap, right? K cap. So first one is over. So similarly, what we have plus Ay Bx into j cap dot I cap plus Ay By j cap dot j cap plus Ay and Bz j cap dot k cap plus let us take the last component. What is that? Az Bx k cap dot I cap plus Az By k cap dot j cap plus Az Bz, right? Az Bz, that is k cap dot k cap. Now we know that, correct? So the dot product of unit vectors in the same direction will be 1. These are perpendicular direction will be 0. So this is 1, this is 0, this is 0. Similarly, this is 0, this is 1, this is 0, sorry, this is 0, here, this is 1. Okay, I wrote it in the wrong direction. So similarly, this is 0, 0, 1. So the 0 means this will remain, this will go off, this will go off, this will go off, and this also will go off, and here this 2 will go off. So finally what you get, tell me?
Ax, Bx.
This is 1, correct? So Ax, Bx plus
Ay,
By plus Az, Bz. So that is the scalar product of two vectors when you write it in terms of, when you resolve it in x, y, z axis, okay, I, j, k axis. There's another interesting property. So we have, suppose, okay, A is a vector. There are 3 vectors, A vector, B vector and C vector. Suppose A vector dot B vector equal to A vector dot C vector. This does not mean B vector is, okay, this doesn't say, this won't say B vector is equal to C vector. This is wrong. You can prove it. What happened? So if B vector is, if the equal vectors, right? When do you call two vectors are equal? They have the same magnitude and the same direction. So if you subtract equal vectors, what will you get? 0 vector. Don't you remember? We did it. Same vector of same magnitude is 0 vector. Correct. So, and okay, so if they are equal, then their difference has to be equal to 0. Correct. So let us see for here. So let us see. So then if I see this equation, I can rewrite this equation, take this left hand side. A vector dot B vector minus A vector dot C vector equal to 0. This is a scalar, the scalar product. So now we know the distributive law of scalar product in law of multiplication. So then what happens? So this can be A vector dot minus C vector. This is equal to 0. Oh yeah, okay. What I say is for A is not equal to 0. I forgot to write that. For A vector is not equal to 0. We are not saying A vector is not equal to 0. So if A vector is not equal to 0, okay, so then what it says is, normally what happens if you write if x into y equal to 0, what you call, if x is equal to not equal to 0, then you say y equal to 0. Correct? But here it is not. Here it is not. This doesn't say it can be B vector minus C vector be equal to 0 or not equal to 0. Why? Yes. If B minus C vector had a direction perpendicular to A vector, then the cos theta is 0. Okay, suppose if you, for example, B vector minus C vector, this is a vector. If this is perpendicular to A vector, okay, so then what happened? A vector dot B vector minus C vector will be A vector into B minus C vector, okay, into cos 90 degree. That is equal to 0. Okay, but we never said B minus C is equal to 0. Okay, so not necessarily B minus C is equal to 0. That means, so B minus C is not necessarily equal to 0. That means B and C are not necessarily equal vectors. They can be unequal vectors. Okay, so that's what dot product. This is very important. Sometimes it gives a confusion. So like normal in a normal multiplicative operation, what do you write? What you say? X y equal to x z, and you tell therefore y equal to z. Am I right? And if you do this here, and then you get a what? Big egg. And down. Okay, so you shouldn't do it. Okay, so that's what. All along in your earlier classes, we never bother about the vectors. So when we have a vectors, you need to really carefully bother about what is the direction. Okay, direction and what do you mean by products, scalar products. So we can. Okay, there is a problem. Okay, I will not do it, but it's very simple. They given two vectors. So they are given two vectors. Suppose, for example, I am giving you a vector. What is that vector? Let me call, this is V1. V1 vector is a resolved vector. That means what they are given, I cap plus 2j cap plus 3k cap and V2 vector equal to 3i cap plus 4j cap plus minus 5k cap. 5k cap. Okay. So we know. We are just, what do you want to say? Find the scalar product of these two vectors. If you want to find the scalar product of these two vectors, we just did, right? So what happened if you had a vector equal to ax I cap plus ay j cap plus az k cap and b vector bx I cap plus by j cap plus bz k cap. So what is scalar product of these two? You remember? What was that? Tell me.
Ax bx plus ay by plus az bz.
So can you tell me what is the scalar product of v1 vector dot v2 vector? Ax is 1.
1 into 3
1 into 3, that is 3. 1 into 3
plus 2 into 4
plus 2 into 4
plus 3 into minus 5.
plus 3 into minus 5, right? 3 into minus 5. So what this will be? 3 plus
8 minus 15
Tell me what it is.
minus 4.
That's it. Okay. So, okay. So in the next class, so this is what all about the scalar product. Next class we are going to see the vector product. How can you multiply two vectors to create another vector? Okay, so when you create another vector, so that vector should have a direction also. Okay, but here we never bother because A dot B doesn't have a direction, just a magnitude. The moment when I go for vector product, the final multiplication should have a direction. Okay, so that we will see it in the next class. Okay.